Okay, so today we're going to start looking at the describing data chapter. We'll finish this on Tuesday, most likely. Away. So, right now we're going to talk about presenting qualitative data graphically. Then later on we'll start talking about quantitative, because that's really, when you think of statistics, we tend to think more of quantitative than qualitative data for the most part. So let's look at our concept here called a frequency table. Well, it's a table with two columns. One column lists the categories and the other one for the frequencies with which the items in the categories occur. Our first example here. An insurance company determines vehicle insurance premiums based on known risk factors. If a person is considered a higher risk, their premiums will be higher. Makes sense, right? One potential factor is the color of your car. The insurance company believes that people with some color cars are more likely to get in accidents. To research this, they examine police reports for recent total loss collisions, and the data is summarized below. So what we have here is our category, which is the color of the car. Color of the car, and then our frequency. And who would have thought that green is the most frequently totaled car? Well, to be honest with you, I would. I have a green car. Anytime I drive it from Fort Walton to here, I'm probably almost hit 4 times every time. You know, you'd think black, but that would be only at night. So that's only half the time, not even half the time, really. Then you might think gray, and I don't see silver on here because it would blend in with the road, but it's green. And in my opinion, it's green because the green tends to blend in with the shrubbery. People don't see my green car. And I have one of them old Souls that were the alien green, so it really blends in with the shrubbery. Which is why I now drive the red one. So another way we can look at the same data is called a bar graph. It's a graph that displays a bar for each category with the length of each bar indicating the frequency. So using the same data, we might draw a bar graph like this. Now our highest frequency was 52, but you might want to think about going a little higher just in case. Plus we can go from 0 to 55 and then have it nice and evenly spaced in 5-unit intervals. Now something I like to do on a bar graph, mainly because I'm not going to take the time to measure exactly, is I would do this. Write the frequency at the top of the bar. That way you know exactly what it's supposed to be. You don't have to, but that is my recommendation. Any questions on bar graphs? A special type of bar graph is called a Pareto chart. It's a bar graph ordered from highest to lowest. So this is the same thing. It's just now we have them ordered from highest to lowest. I mean, in the case of this, if I was somebody at the insurance company, I'd want to be able to tell right away what's the worst car to drive, what's the worst color car. So having it listed highest to lowest, I can see. And here we have in a survey, adults were asked whether they personally worried about a variety of environmental concerns. The numbers out of 1,012 surveyed who indicated that they worried about Worried a great deal about some selected concerns are summarized below. So we have the issue and we have the frequency. Then we can take this data and put it in a bar chart. Same data. Easier to see how everything fits as opposed to looking at a bunch of numbers. But again, it's a matter of how you better see the data. General public prefers pictures, so that's why we give them pictures. A table with numbers, most people will turn the other way. Which brings us to our next one, a pie chart. Pie chart is a circle with wedges cut out of varying sizes, marked out like slices of pie or pizza. They always mention pizza. Relative sizes of the wedges correspond to the relative frequencies of the categories. So here we are looking at our total loss collisions again. Note they've color coded it as well, green, red. They've also listed the colors out here and the frequency. Because can you really see a difference between blue and green just by looking at the pie piece? Kind of hard to see. Another issue with these is it's almost impossible to freehand draw. So yeah, you'll see them a lot because they look pretty. Now, if you go into statistics, though, one of the things you'll be taught is colors like this. Too much stuff distracting from the data. Of course, that may actually be what the thought was. Let's distract people from what it's saying here. But we don't get that deep into this. So here we have another representation of a pie chart. In this chart, we show percentages of voters supporting each candidate running for a local Senate seat. So if we had 20,000 voters in the district, pie chart shows that 11% of those, which would be roughly 2,200, support Reeves. So again, there are colors to differentiate. We also list who each one represents, and we also list, in this case, the proportion, the percentage of people that voted for them. I mean, we could just as easily have wrote this as Ellison, 46%. Douglas, 43%. Reeves, 11%. Same information, but it doesn't look as pretty. And it's all a matter of who you're showing the information to as to how you will display it. Next, we have what's called a pictogram. Pictogram is a statistical graphic in which the size of the picture is intended to represent the frequencies or size of the values represented. So in this particular pictogram, a labor union might produce the graph below to show the difference between the average manager salary and the average worker salary. So without reading any further, what do you think the comparison is? About 4 times as much? This volume looks about 4 times this volume, right? Or area. Well, that's the thing. First thing to note is the labor union did this. So labor union, they represent the workers. They want you to think the managers make a whole lot more than the workers. So it looks 4 times as large. However, the actual graph, and you see it's not fibbing because you did it accurately, is height. Still 2 times as much. But that's not as bad as 4 times as much. So one of the things we have to watch out for when we look at graphical representation is things like this. How is it displayed? Find out what means what. Is this by height? Is this by area? Or is it just a pretty picture? Another way, I think the saying is statistics don't lie, statisticians do. Or actually, it's the people that use the statistics more than the statisticians. So here we have two graphs showing support for same-sex marriage rights from a poll taken in December of 2008. But notice the vertical scale. This one starts at 0 and is nice and evenly spaced out by 5. I guess that's percentages. This one, however, starts at 40. Now, if you were to look at this graph here, looks kind of close, fairly evenly. Yeah, a little more oppose it than support it. But then if you look at this graph, what do you think about that one? One, two, three. This looks like this one looks 4 times higher than this one. Right? However, this is roughly 45 and this is 55. Just like this was 45 and 55. So just a presentation makes it look like there's a bigger difference than there is. It's not lying to us, it's misleading us. Those are things you have to be careful to see when you're looking at things like this, and also when you're creating things like this. Is there some way that somebody can misinterpret this chart? So any questions on the representations of qualitative data? Different ways it's done. So now let's get to the good stuff. Quantitative data. So a teacher records scores on a 20-point quiz for the 30 students in this class. The scores are, and here's a list. We want to summarize these results in a frequency table by grouping like values. So I start out with how many zeros do I have? 1, 2. And I think I only have 1, 5. How many 12s? Just the 1? How many 15s? 1, 2. How many 16s? 1, 2. 17. 1, 2, 3, 4. 18. 1, 2, 3, 4, 5, 6, 7, 8. 19. 1, 2, 3, 4. And 20. 1, 2, 3, 4, 5, 6. So there should be 30 students. So if I add this up, 2, 3, 4, 6, 8, 12, 20, 30. So I'm good. We've just created our first frequency table using qualitative or quantitative data. And we can create a bar chart using this, like this. If somebody made a typo. This is a bar chart. Not a histogram. That's coming up next. Any questions on how we did this? So this is what? 2, 1, 1, 2, 2, 4, 8, 4, 6. To clarify. Don't have to do that, but it's helpful. Everybody good on bar charts with qualitative data or quantitative data? Now, since this is quantitative or numerical values, it doesn't make sense to do a bar chart. First and second bars are 5 values apart. The later bars are 1 value apart. It'd be more correct to treat the horizontal axis as a number line. This is called a histogram. Histogram is like a bar graph, but where the horizontal axis is a number line. So you see we have 0, 1, 2, 3. Every number is accounted for. Then we have the frequencies. And notice they're touching. In a bar graph, they don't touch. Or bar chart, they don't touch. Now, this is fine when I don't have a whole lot of different data points or a very wide spread. If I have a larger spread of data, I may want to do what's called class intervals, which are groupings of data. In general, we define a class interval so that each interval is equal in size. So if the first interval contains 120 to 129, second in class would contain 130 to 139, and we try to have between 5 and 20 classes, typically depending on the number of data we're working with. So, suppose we have collected weights from 100 male subjects as part of a nutrition study. For our weight data, we have values ranging from a low of 121 pounds to a high of 263 pounds, given a total span of 142. Now, we could create 7 intervals with a width of 20, or 14 intervals with a width of around 10, or somewhere in between. Sometimes you have to experiment to find the best possible width. So we'll try using an interval width of 15. We could start at 121 or at 120 since it's a nice round number. So here's the thing to notice. How wide is that interval? Did you say 14? No, we want 15. But think about this now. That interval contains 120, 121, 122, 123, 124, 125, 126, 127, 128, 129, 130, 131, 132, 133, and 134. Now, how many different data points are in that interval? 15. The way to find the width of the intervals is you can start with the first, the lower number to the lower number. 135 minus 120 is 15. Or the higher number to the higher number, 149 minus 134, 15. So if we were to start at 121, our next interval would start at 136. So this would be 135. And then we'd continue. We'd have 151, that'd be 150, be 165, and then so forth. Any questions on how that is done? Again, sometimes you have to play with it. Depending on how spread out your data is, you may need more intervals, or it might be best to do less, depending. So here's what the histogram will look like. Notice we have our frequencies down to the side. Here we have our weight, and this is a number line. It's continuous, it doesn't stop. This first group is starting at 120 and going to, but not touching 135. And that was 4, just like our frequency table said, and so forth. Any questions on how this works? So here we have data below came from a task in which the goal is to move a computer mouse to a target on the screen as fast as possible. On 20 of the trials, the target was a small rectangle. On the other 20, the target was a large rectangle. Time to reach the target was recorded on each trial. So we have the intervals with a width of 100. We have the small target frequency here, large target here. So we could represent this data with a comparative histogram or bar chart like this, where you see the small targets in blue and the large target is that maroon. Maybe something like that. But that's really hard to see much with. I mean, you can look at it and figure it out, or we can move to the next concept called a frequency polygram. Frequency polygram starts out like a histogram, but instead of drawing a bar, a point is placed in the midpoint of each interval at height equal to the frequency. Typically, the points are connected with straight lines to emphasize the distribution of the data. So now we can compare them a little easier. I can see this purplish color is the large one, and as you can see, more people did the large one in the shorter times till we get here to 650, then it goes the other way. And of course, by 750, everybody's already hit the large one. So it's easier to compare the two using this method as opposed to side-by-side bars. So any questions on anything we've done so far? Graphical representations. So now we can get to the mathematics portion of the program. So what we're going to be looking at next is measures of central tendency. What we're talking about is we have all this data, where's the middle? And there's 3 different measures we look at. The first one is one you've probably heard of, but by a different name. The mean, or the arithmetic mean, of a set of data is the sum of the data values divided by the number of data values. You've probably heard it called average. So basically the mean, and typically it's either mu, sometimes x bar. Essentially mu is for population, x bar is for samples, is equal to the sum of all the x's over n. In this case, mu is our mean. X is data points. N is the number of data points. And this symbol here, the sum of all x's, means add all data points. So looking at my formula, I need to find the sum of all the x's, which is 79 plus 86 plus 82 plus 94. And we get 79 plus 86 plus 82 plus 94. This is equal to 341. Then n, the number of data points, is simply 4. So mu is equal to the sum of all the x's over n, which is 341 over 4, which is 85.25. Any questions on how we did that? Everybody good? Okay. So the number of touchdown passes thrown by each of the 31 teams in the National Football League in the 2000 season are shown below. So I know N equals 31. What's the sum of all my X's? $37, $33, bless you. 29, 28, 28, 23, 22, 21, 20, 20, 19, 19, 18. There are 4 18s. 16, 15, 14, 14, 14, 12, 12, 9, and 6. I think I messed up somewhere. I'm sorry? That's not what I got. Did I throw a multiplication in here somewhere? I got 2614. Anybody else got something? As the mean, but what was the sum of all X's? I got 26. I know that's not right because I got something. I got your 592. We got a 2614. You said what was your mean? Yeah. I think 20.5 is right.
I think just multiply it by.
Yep.
634.
So then we have mu is equal to 634. I think we both missed some. I hit a multiplication somewhere. And that comes to 20.5, you said? This is what blows my mind. I don't know if we have any football fans. What the record was just broken a couple years ago. It was over 50 touchdowns in a season. And it was a team, entire team, not just one quarterback. They only threw for 6 touchdowns in a whole season. Must have been Cleveland. No, wait, they didn't exist in 2000. That's why there's an odd number. So any questions on how we did this? It does get a little.
What?
I'm trying to think. I don't think there's.
Oh, it's okay. I'm not concerned.
I don't think there's any.
Oh, I know all the stuff that they're doing right now. No. Yeah. Hi.
There we go. There.
Are you outside?
All right. So this is fairly simple. Add it all up, divide by how many they are. The only problem is making sure you add them all up right. And as you see, we got 3 different answers by 3 different people. So my first thing to say on this would be, show me this. Whatever you got. So you got 592. Just tell me the sum of x's equals 592. Because then I'll see your only mistake was that you made a calculating error when adding them all up. And with 31 data points, it's real easy. Because I got 2,600 for some reason. No idea why.
It's a lot.
There must be a multiplication in here somewhere or something. Hard to tell. So be careful. Don't be afraid to show me some stuff so So now we get to a frequency table. We have 100 families in a particular neighborhood are asked their annual household income to the nearest $5,000. The results are summarized in the frequency table below. Find the mean household income. So we know N is 100. Now, what this frequency is saying is 6 families made 15,000 a year. So to get all of our data, we could write 15 6 times and add it all up, but we can make it easier on ourselves. 6 times 15 equals what, 90? Do the same thing here. 8 times 20 equals 160. 11 times 25, what's that, $2.75 for 11 quarters? 17 times 30, I think that's 510. 19 times 35, well, 20 times 35 is 700 minus 35, 665. 20 times 40 is 800. 12 times 45 is what? 450 plus 90 or 540. 7 times 50 is 350. Then all we have to do is add up those numbers instead of adding up 100 individual things. So we have 90 plus 160 plus 275, 510, 665, 800, 540, 350. And I still 3,390, and I got the wrong answer. I know that's the right answer because I remember it. So the sum of all our x's is 3,390. So to find our mean, we simply take sum of the x's over n, 3,390 divided by 100, and we get 33.90. That is our mean. So as far as a measure of central tendency, a mean can be very good, depending on what the data looks like. Which brings us to this little addition. So let's extend the last example. Suppose a new family moves into the neighborhood and has a household income of 5 million, which is 5,000. So let's add this to our sample and calculate the new mean. And I'm just going to do it on the previous page. And make a note so next time I'll know what happened. So there's this one family that does this. So what's my new N? 101. What's my new sum of all the x's? Well, this is the sum before. I'm going to add 5,000 to it. So that gives me 8390. So what's my new mean? I get 83.07.
Where'd that extra 1 come from?
The next question says to add a new family to the neighborhood.
Oh, okay, I see.
And the purpose of this is you see that one family that's way outside what everybody else is, increase the mean by 50. So while the mean can be a good measure of central tendency, as you'll see in if you go on in statistics, It can also be easily affected by what's called an outlier, something way outside all the other data. So we have to be careful with that. Any questions on the mean and how to calculate the mean? How to calculate the mean from a frequency table? So next time, I think we'll talk about the median. We'll put that off till Tuesday. Unless anybody just really wants to start talking. Let's see, is the roll sheet still out there somewhere?